Well, let's talk about properties of logarithms. The base, we're talking about the log base b of x equals y. And keep in mind, this means exactly the same thing as b raised to the y equals x. So first of all, the base has to be a positive number, not just 1. It can't be 1 because 1 raised to any power would just be 1 all the time. It wouldn't be a function because your x values would all be 1, and they would lead to an infinite number of y values. So this would not be a function if b is 1. And if b is a negative number, then if you've got, say, -2 raised to an even is positive, -2 raised to an odd is negative, and that's easy to figure out if your exponents are integers. But then what happens when your exponents, get to be other things? So let's don't even go there. It would be jumping back and forth all over the place. So the base has to be a positive number and not 1. The logarithm, the number over here, y can actually be any number because you can raise your base up to any exponent. You can use any exponent at all. You can have 2 raised to a negative power, 2 raised to a positive, 2 raised to a fraction, 2 raised to an irrational number. You can have 2 raised to the square root of 3. If you don't believe me, punch it into your calculator and see whether it gives you an answer or an error message. However, the number you're taking the log of, the x, has to be positive, because since your base has to be positive, there's no way to raise a positive base to any exponent and get a negative answer. If the exponent graph looks like this, where the domain, if we've got y equals a to the x, your domain here is all real numbers. But your range would have to be numbers greater than 0, because you can't get any negative results here. On the other hand, and let me erase some of this to have a little bit more space here. If we're graphing the inverse of this, remember that an inverse is going to be switched over this point, this line, x equals y. So this point ends up over here, this point ends up over here, this point ends up over here, this one ends up over here, this one ends up over here. The graph of the logarithm looks like this. The domain of something like this, so now it goes from having the point 0, 1 to having the point 1, 0, and everything switches. This point 2, 8 becomes the point 8, 2. Remember, everything switches. So the domain is now the range. So now the range is all real numbers. And the domain is now from 0 to infinity. So now the domain is restricted and the range is not. Okay, so let's actually get into the rules. no matter what your base is, if you're taking b raised to the exponent 0, the answer is always going to be 1, right? Anything raised to the exponent 0 is 1. So the log of 1 is always going to be 0. You can't take the log of 0. You could take the log of your base itself. What exponent would you have to put on the b to make it equal b? Well, a 1, of course. These three are based on your exponential laws. Now remember that a logarithm is an exponent. And if x raised to the a times x raised to the b is x raised to the a plus b, if when you're multiplying the bases you add the exponents, and your logarithm is the exponent, it turns out that the log of a times b is going to equal the log of a plus the log of b, and this is to any base, and I already used the b, so let me just like put an x in here to represent the base. The log of a product is the log of the first one plus the log of the second one. So if you wanted to find the log of, I don't care, any base, of 2 times 3, you could do the log of 2 plus the log of 3. The quotient rule, if you have the log of a over b, a fraction, just like your exponents, the exponents in a fraction, x raised to a power divided by x raised to a power, you subtract your exponents. So if you've got the log of a fraction, you can do the log of the top minus the log of the bottom. And a power to a power means multiply your exponents. So log of a raised to the b, well, that turns out that you can bring the exponent down in front, and it's b times the log of a. There are a couple more rules. If we have b raised to the exponent log base b of x, that turns out to equal x. Now that's kind of hard to see, but remember that the log base b of x is the exponent, the value of this exponent is the exponent you have to raise b to make it equal x. Therefore, b is raised to the exponent that makes b equal x. Let me say that again. The log base b of x is the exponent that you have to raise b to make it equal x. Therefore, b raised to the log base b of x is the same thing as having b raised to the exponent that makes b equal x. So if b is raised to the exponent that's going to make it equal x, the answer is going to be x. We don't have to know what the log is in between. Furthermore, the log base b of b raised to the x. This is going to equal, if I bring the exponent down in front, this is going to equal x times the log base b of b. But we already know from rule 2 that the log base b of b is equal to 1. So this is equal to x times 1, which is just x. So if b is raised to the exponent base b, this is the answer. If you have the log base b of b to a power, this is the answer. So the log base 5 of 5 raised to the 4th is 4. On the other hand, 5 raised to the log base 5 of 4 means 5 is being raised to the exponent that's going to make it equal 4. Don't know what the exponent is, but the answer is going to turn out to be 4. So these are your main exponent logs. And these 3 are what we use to expand and condense different phrases, different exponents that involve logarithms. Let's say we have the log of AB over C, base, I don't know, Z. I already used the B. So we could say this is the log of the top minus the log of the bottom. So it's the log base Z of AB minus the log base Z of C. The log of A times B is going to be the log of A plus the log base B of B, and then we've got minus the log base C of C. If you're taking the log of a fraction, all of the logs of the things in the numerator are going to be positive, and all of the logs of the things in the denominator are going to be negative. Furthermore, if you have exponents in this expression, let's say we have a cubed on the square root of b over c to the 5th d. The exponents are going to come down in the front. Now b to the square root of b is the same thing as b raised to the 1/2. So this one's going to be positive, this one's going to be positive, this one's going to be negative, and this one's going to be negative because you have to carry the negative through. So I can do this piece by piece to show you. This is going to be the log base z of a cubed, and I'm going to rewrite this as b raised to the 1/2. That's the exponent that's identical to the square root, because this is the square root of b raised to the 1st. So it's going to be minus the log base z of c to the 5th times d. These two I can add. So I've got the log base z of a cubed plus log base z of b to the 1/2 minus the log base z of c to the 5th. Well, this is minus this whole thing. So this would be minus parentheses or brackets. This would be the log of c to the 5th plus the log of d. So this negative has to be carried through. So bringing the exponents down in front, I've got 3 times the log of z plus 1/2. Sorry, I left out the a. Can't do that. Plus 1/2 times the log base z of b minus 5 times the log base z of c minus the log base z of d. So I can look at this and say, well, I had an a cubed in the top. I had a b to the 1/2 in the top. I had a c to the 5th in the bottom. And I had a d to the 1st in the bottom. So I could put this all back, or I could take it apart as, okay, the a cubed is in the top. B to the 1/2 is in the top because it's got a positive log. C to the 5th is in the bottom. And D to the 1st is in the bottom. I just didn't bother to rewrite the B to the 1/2 as a square root. So you can learn to take these apart really quickly, and you can learn to put them back together really quickly. It's just a puzzle. Don't try to make something hard out of it. It's not so bad. A little bit of practice and you'll have this definitely under control.